Hello everyone, I'm Afsoon Yousefi and I will go through the method we proposed in genetic programming for cost-sensitive control in resource-constrained sensor systems. So what do we mean by cost-sensitive control? Let's go through an example. Suppose we want to measure the amount of water in a snowy field once a day for a whole year, and we have three sensors available. Sensor 1 is a sonar that measures depth of the snow at a single point. So the error is high, but it's pretty cheap. Sensor 2 is a gamma ray detector that measures water content at a single point, so the error is a little better, but the cost is higher. And sensor 3 is a LiDAR that is able to generate 3D sensor profiles, so it's pretty accurate, but the cost is really high. So if I want a model that is able to predict the amount of water for the future or any other output, and I want it to be accurate as well as low cost, what should it be? Which subset of sensors should it use? Should it always use sensor 1 so it's cheap? Should it always use sensor 3 so it's always accurate? Or use sensor 2 so it balances error and cost but ignores the fact that there is a very cheap sensor available or very accurate sensor available? Which subset of sensors should the model use? Previously, genetic programming has been used to find these kind of models. So it trains models using a pre-gathered data set from the field, and it considers some optimization objectives. For example, in here, we need to consider error, minimize the error, so the model is accurate. We need to minimize the cost, so the prediction of the model is low cost. We need to minimize the size, so the model is not overfitted, and we need the models to be selected from a very diverse set of models, so it's not from a local optima. As you can see, there are 4 objectives that has to be considered, and based on the curse of dimensionality, we know that it is not practical to have more than 3 objectives. So this is the first problem. And the second problem is that these models are static, so it's always going to use, for example, in this situation, sensor 1 and sensor 2. But we want the models to be dynamic because, for example, in a situation that the weather has not changed, then a low accurate sensor would answer perfectly. But if the field is really changed, then we need to use a very accurate sensor, so it's going to capture all the changes. So we need the models to be accurate. To answer these 2 problems, we came up with a non-hierarchical method, which is basically an enriched genetic programming which has if statements and comparison. So it's able to come up with these kind of structure that is going to select on the sensors that has to be pulled based on some conditions, and the genetic programming has to find these conditions. And also, in order to answer the curse of dimensionality, we reduce the number of objectives to 2. So the first one is error, and then the second one is the product of cost, size, and 1 over diversity. So in optimization process, we're going to consider these 2 objectives, and after the training, we're going to decide the model that balances error versus size times 1 over diversity times cost, and then the cost of each measurement is the aggregated cost of the sensors that has been pulled based on the conditions inside the model. So Now we have answered to those two problems that genetic programming has. The problem with this is that adding the cost to an already complicated problem makes it even more complex. So what should we do? That's why we came up with this hierarchical model. So the way it works is that in the first round, we're going to train models having just sensor 1 available, which is the cheapest sensor and lowest accurate sensor. We train genetic programming models not considering cost at all, and then at the last we're going to select the top portion of the models based on the error and put them in ensemble 1. In the second round, we're going to add sensor 2, which is the next expensive, next accurate sensor to the available set of sensors, train models, again not considering the cost, and again selecting the top portion considering the error, put them in the ensemble 2. And in the last round, we're going to have all the 3 sensors available, train models without considering cost, and put the top portion of the models which has the lowest error in ensemble 3. Now we have ensemble 1, which uses sensor 1, ensemble 2, which uses sensor 1, sensor 2, and ensemble 3, which uses all 3 sensors, and put them in this hierarchy. Layer 1 has ensemble 1, layer 2 has ensemble 2, layer 3 has ensemble 3. And based on some conditions, we're going to start with the cheapest ensemble, which is layer 1. And based on some conditions, we have to decide on if we need to go to a more expensive, more accurate ensemble or not. If no, the mean of predictions of ensemble 1 is going to be accepted. Otherwise, we're going to use ensemble 2. Again, based on some conditions, we're deciding if we need a more accurate ensemble or not. If not, the mean of the prediction is going to be accepted. Otherwise, we're going to use ensemble 3, which has all the 3 sensors available to it, and then accept the prediction of that ensemble. So what should these conditions be? Suppose we have an expert committee, and we're going to ask them a well-known problem that they have seen before or a very similar one. Then their answers is going to be very similar or exactly the same. But if I'm going to ask them a question that they have not seen before, then their answers are going to have a high variance. This idea has been used as an uncertainty indicator in a paper named Query by Committee, and we have adapted this idea into our problem. So suppose an ensemble is an expert committee. Each model in that ensemble is a field expert, and the training data is the field knowledge that they have been trained on. And the testing data then is going to be the new problem that I'm going to ask them. So if in an ensemble I ask a testing data, and then the variance on the prediction is higher than the variance on the training data, it means that they have not seen that problem before, and it's not in their field knowledge. So they need to go and use a more accurate, more expensive ensemble that has a wider field knowledge and has more variety of sensors available. Now, if you have a lot of budget and you are confident that you can pay a lot of money or a lot of power or a lot of time, then you have lower tolerance for disagreement and error. And you say, okay, I have a lot of money and I can use more expensive sensors, but I want it to be accurate. But if you are lower on budget, then you say, okay, I have higher tolerance for disagreement and error, but I want lower usage of the expensive sensors. In order to have this in our models, we have introduced tolerance parameter from 0 to 1. And by adding this term to the conditions, we say if you are high on budget, then decide on a lower tolerance parameter. So in this condition, with this condition, it has higher probability to go and use a more expensive, more accurate sensor. But if you are lower on budget, then you need to decide on a higher tolerance parameter. So the probability of going to a higher layer is going to decrease. We have tried these two models on synthesized data. So we have three sensors. Sensor 1, which has a very complex relation to the ground truth G, but has the lowest cost. We have sensor 2, which has a less complex relation to ground truth G and has a medium cost, and sensor 3 that can measure ground truth G perfectly but has the highest cost. The training size was 150, the testing size is 50, and we have tried a hierarchical method with different tolerance parameter from 0 to 0.8. And non-hierarchical method had a population size of 100 and it was trained for 300 generations. In hierarchical method, for each layer there was a population size of 100 and each layer was trained for 100 generations. So the total amount of training is 300 for both methods, and it is fair. In here you can see the error rates for non-hierarchical method and hierarchical method with different tolerance parameters. So as you can see, when the tolerance parameter is high, it means you are low on budget, then the error is higher than the non-hierarchical method. But as the tolerance decreases, which means your budget has increased, then the error rate is going to be comparable to the non-hierarchical method or even lower. In here you can see the average cost for non-hierarchical method and hierarchical method with different tolerance parameter. As it can be seen, when the tolerance is high, which means you are low on budget, then the cost is lower. But as the tolerance decreases and your budget increases, the cost gets higher and higher, but it never reaches the cost of non-hierarchical method. In here you can see the p-value comparing non-hierarchical method with hierarchical method for different tolerance parameters, and the red portion is when the non-hierarchical method did significantly better than the hierarchical method. The blue portion is where there was no significant difference between the non-hierarchical and hierarchical method, and the green portion is where the hierarchical method outperforms the non-hierarchical method. So as you can see, the hierarchical method wins over the non-hierarchical method, except for these two setups where the tolerance is really high, which is when you are really tight in budget and you are willing to sacrifice a little bit of accuracy in order to have really significantly lower budget. In here you can see that we have tried these two methods on actual data from UCI repository, and we have sorted these datasets from dataset 1 to dataset 10 based on the number of instances inside the datasets. We have partitioned these datasets into halves. The first half has been used for training, the second half has been used for testing. The non-hierarchical method has been trained for 200 times the number of features, and then the hierarchical method, in hierarchical method each layer has been trained for 200 generations. So again, the amount of training for non-hierarchical and hierarchical method has been the same. We also calculated the accuracy of each sensor predicting the outcome using linear regression, and then considered that as cost, which is rational. So if you want a more accurate sensor, you need to pay more. And in here you can see the error rate for non-hierarchical method and hierarchical method and p-values, comparing them together. So the red portion is when the non-hierarchical method did significantly better, and the blue portion is where none of them outperforms the other. And if you pay attention to the error rate of non-hierarchical and hierarchical method, we can see as the datasets grows bigger, the difference between the non-hierarchical and hierarchical error rate decreases, and even in the bottom three datasets, which are the biggest datasets, the hierarchical method was able to reach even lower error rates. In here you can see the cost rate for non-hierarchical method and hierarchical method. The red portion is where the non-hierarchical method did significantly better, and the green portion is where the hierarchical did significantly better. So if you pay attention to dataset 3 and dataset 6, you can see that these datasets had sensors or features that had really low accuracy, for example 0.0002, or even non-informative at all, which had accuracy of 0. And these are the datasets that non-hierarchical method did better in terms of cost. In general, based on the experiments we had with synthesized dataset and real datasets, the hierarchical method was able to reach significantly lower prediction cost compared to the non-hierarchical method. And as the datasets grows bigger, the hierarchical method was able to achieve competitive and sometimes even lower error rates. And I have to mention that these datasets was from very different fields, and it shows that this method is like general and could be applied to any method considering any kind of cost. And for the future work, we want to consider some kind of dynamically tuning the balance and the cost. So if in the middle of the measurement and prediction, the budget, for example, changes, or for example, there has been some days of cloudy days and the power was not able to charge, so it's able to tune dynamically. And also we want to consider an online learning, so the models are able to adapt to changes during the measurement. We also want to apply this method to a real resource constrained sensor system that is deployed inside the field. And thank you for your attention, and I apologize for any inconvenience. I was not able to attend the conference. Thank you.